we ended on Thursday of last week was looking at atomic radius. So we just mentioned the trends, and I didn't actually show you any pictures. So your textbook has a nice table, a pretty image that shows these trends. And as you see, as we move down a column, in every single one of these columns, what happens to the radius? It gets bigger and bigger. Right? And the reason we came up for this was what? Why does it get bigger as we move down a column? What's happening as we move from hydrogen to lithium, lithium to sodium? The atomic number changes. So what happens when we change the atomic number? What are we changing? Number of protons. Right? And our protons, along with our neutrons, are found where? In the nucleus. Right? If we think back to that example that we talked about, dang it, in our earlier stages of our atomic structure, our nucleus was the size, if we scaled this up, we made the nucleus the size of a marble, the size of the atom was the superdome. Okay, so yeah, as we move down a column, I agree, the protons do increase, the neutrons do increase. But is that the largest contributor to the size of an atom? It's the electron count that's really changing. And so when we go down a column, okay, at least initially, we're looking at neutralizing that positive charge of our nucleus. So we're adding more electrons as well as adding more protons. So when we're looking at the atomic radius for any one of our elements, as we move down a column, yeah, we're increasing the atomic number, but at the same time, we're increasing the amount of electrons, which means the more electrons, the bigger our atom necessarily has to get, because our electrons need to get further away from each other. So down a column, it makes a lot of sense. It gets bigger because the electrons need more space to occupy, so that kind of expands outwards. Everybody okay with that analysis? Right. So what would happen if that analysis was true? What do you think would happen as we move across a period from left to right?
You would suspect it to get bigger.
Right. As we move left to right, what's happening as we move from lithium to beryllium or beryllium to boron? We're adding protons and we're adding electrons. Well, if we add electrons, what should happen to the size? They should get bigger. What trend do we actually see? It gets smaller. Right? That's kind of an odd trend to explain. So before we can actually explain that trend, we have to know something about where our electrons can exist. Right? How do our electrons fit in the atom? And all we've really said is they're somewhere on the outside. Right? And if we just said more electrons, more space, then as we move left to right, we should expect it to get bigger, and it doesn't. So there's something else going on there. Okay? And that something else going on takes us back to chapter 4. Okay? So we got atomic radius up through chapter 5, and then we have this weird explanation or this weird inconsistency with atomic radius. That puts us back into chapter 4 to explain what's going on with electrons. Okay? So before we make that leap back to the second half of chapter 4, questions about atomic radius? General trend within a column makes sense at least. Okay?
Wait, so, sorry.
No, that's fine.
So they do get smaller.
They do indeed get smaller.
Both
which
ways?
is
Down.
no, down a column, it gets bigger. Left to right, we would predict it to get bigger. It does not get bigger. Okay, it gets smaller, which is very non-intuitive. That doesn't make any sense according to our understanding so far. There has to be something weird happening with our electrons to allow it to get smaller as we add more electrons from left to right. Okay, so that doesn't make sense. Yes?
So according to the table, then helium is the smallest of all of them? Since we're going to the right and we're up high?
Your hydrogen and helium are a little bit weird in that respect because they're so small. Helium, I think, is slightly smaller than hydrogen, but not by much. If we look within your trends, so what your textbook gives you, you'll notice that do you see hydrogen or helium? They aren't on that table, and that's because we can't explain that trend quite as cleanly. Okay, the other trends are a little bit easier to see. Which is the trends that you'll be expected to predict is out of these sections of the periodic table. which may bring in your next question. Yes?
Well, it's not really a question, I want to clarify something. So it's like a parabola with this electron thing. So it gets bigger, and then it gets smaller, and then smaller, bigger, in the middle.
If you,
Left and right.
so as you just go left to right, it just gets smaller. Okay, so you can't look at the periodic table for this. For our atomic radius, if we look at our radius, left to right, lithium is 0.152, beryllium is 0.11, 0.08, 0.07, 0.07. Okay, it's getting smaller all the way across. Okay. So kind of back to the hydrogen-helium issue. You'll notice that on this table, you don't see titanium, or cobalt, or nickel, or iridium, or lanthanum, or plutonium. Right? When we're looking at these atomic radii, we're only predicting in the first 2 columns and the last 6. Okay? That's where you're expected to understand your atomic radius. So you can ignore the transition elements, and you can ignore the inner transition elements. Okay? So you don't need to worry about those when predicting size. Okay? Another way that we can look at this is we can compare atomic radius and metallic character, because we've looked at metallic character before, our most metallic being our lower left, and our least metallic being the upper right of our periodic table. Okay? And we can see how that transitions in comparison to atomic radius. Okay? You get a very similar comparison. Okay? And that's what this chart is trying to show, and the height of each of those things is supposed to represent their atomic radius and their metallic character. So metallicity and atomic radius track with each other. They have the same trends. Okay? So into chapter 4. Chapter 4 really kind of brings up this concept of light and the wave nature of light. And that's because really when we look at electrons, electrons have kind of a particle characteristic and a wave characteristic associated with them. Okay, so we have to understand something about waves when we're looking at our electrons. That's where a lot of the science came from. Okay, so light passes as a wave through space. And because it has a wave, there's certain characteristics of it. You can get wavelength and you can get frequency. Okay? The relationship between those is shown kind of in these graphs. So in our red line, we have a long wavelength. So we go peak to peak. The distance between those peaks is relatively large. So we say that distance is a long wavelength. And the blue one down below, in our peak to peak distance, is now much smaller. So it has a smaller wavelength. If we look at the frequency is now comparing a standard, typically time measurement. So for an interval of time, how many of these peaks pass. Okay? And so what they're trying to do, sort of, if that's my interval of time, okay, which of these has a higher frequency? So frequency is the number of peaks that occur effectively within that unit of time. So within those 2 blue lines, which of those has the greatest number of peaks? Bottom one. So the frequency is higher in the lower one than it is in the upper one. Okay? And we can look at a relationship between wavelength and frequency, bringing in all sorts of fancy equations and energy, which is sort of relevant, but we'll kind of leave it alone because you don't ever really need to worry about it. We'll leave that for 151 to bring in those calculations. Okay? So you don't need to worry about the calculations. You just need to see that we have this kind of inverse relationship. The next part of this is energy. Okay? Light is part of the radiant energy spectrum, which is really fun because everybody panics. Oh, radiation, it's the worst thing ever. Well, for us to see, we are seeing radiation. Okay? It is wave energy forms. And our eyes happen to respond to certain energy wavelengths. That response is then triggered in our brain for different colors, okay, and how we determine things, okay, or how we visualize things. So vision is ultimately a section of our radiation spectrum. Okay? And within this spectrum, we're looking at different energies associated with them. So at the bottom there, you can see the visible spectrum. We've got the nice bright colors, purple all the way to red. Right? And within that visible spectrum, what they're really trying to show is that that section of energy, or radiative energy, is only right there. And as far as our overall understanding of energy, or particularly wave energy, it's a very small section of the total possible radiative energies. Okay? Why do we have it subcategorized out into separate sections? Because ultimately this is just a spectrum. And this is kind of another weird thing. Why do we call the visible spectrum? Because you can see it. Okay? And when we look at the visible spectrum, do we just say, oh, we just have the visible spectrum, it's here? Or could we further subcategorize this into different things? What could we subcategorize the rainbow into? Into the individual colors. Okay? Red, orange, well, that's not orange. Let's try that again. Orange, yellow, green, blue, indigo, violet, right? So you've got those individual colors separating out of it. But where does it transition between red and orange? Okay, where's the definitive line where to the right of that line it's red and to the left of it it's orange? Okay, there was a good answer that I heard floating around some over here. There isn't. Okay, it's a complete spectrum. So when we go back up to the spectrum and we look at all the possible energies or forms of radiation that come out of our ultraviolet spectrum, those subcategories are like the red, orange, yellow, green. Okay? Anything on that borderline between those isn't really a sharp line. It just kind of depends on what seems to classify it best. Okay? So we've kind of come up with these terms. Within that, we might want to come up with something about energies. Okay? So let's, in theory, ignore where it says any information about energy. Okay? And we look at our spectrum. Which end of that spectrum has the higher energy? Okay, why is the violet side higher in energy? Okay, well, we could look at more peaks. That's an interesting idea. Never thought of it that way. Okay. It has the most energy there, but if we look at the names, okay, which one are you more afraid of impacting you? Okay, cosmic rays. Maybe you don't know cosmic rays. Maybe you know gamma rays. Okay. Why would gamma radiation be potentially problematic? The Hulk, that was not a particularly pleasant experience. Okay? If you still don't know that because you don't read comic books, that's fine. You might run into X-rays. Okay? Are X-rays potentially harmful?
Yes.
Yeah. Okay, so we at least hit one that we relatively all agree on. X-rays are harmful. Radio waves. We don't really care about radio waves. Okay, so if we look at relative energy, we can compare that and make rough approximations to saying that we're looking at relatively low energy down here. That says energy. And high energy up here. This can give us some more information about the visible spectrum. Which is the highest energy of our visible light? Okay, as a hint, that spectrum is supposed to be neatly inserted, compacted, and inserted directly into that visible section. Which end of that has the highest energy? Which end is closest to the highest energy? The violet end. Okay. What we're looking at for our highest energy light is violet. Our lowest energy? Now the red. Okay. So some questions that could get tossed out of there, or tossed into this. Which has the highest energy? Red, yellow, or I can read red, green, blue, yellow. Okay. Which of those has the highest energy? Blue. How would you know that? So I'm here comparing to the spectrum. I agree with that. That's a nice, reasonable thought process. Except on an exam, more than likely, what do you see? How do you know Which has the higher energy?
Darker colors.
You're going to have something memorized. Okay? Darker color. I've never thought of that one. That does kind of work, sort of. What I would recommend, wrong button. What I would recommend you do, as I kind of alluded to at the bottom, is that you memorize or come up with some way to remember the visible light spectrum and the colors within it. Okay? The one that most people seem to remember, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Okay? The next part of it that I tag onto this is trying to pick up something about the energy. Okay? If we look just outside the visible, we run into ultraviolet or infrared. When you walk outside, which energy are you more concerned about? Ultraviolet. Why? High energy. Which is closest to ultraviolet? Violet or red? Violet. That says that this end is my ultraviolet, this is my high energy, this is my low. I now have a way to classify that so that when I get to a test, I can write out my Roy G. Biv, remember this whole ultraviolet deal, and I can now drop in this high-low energies.
Question.
You might see where you're going with this, but go ahead.
Okay. With the microwaves, essentially we're cooking our food with microwaves, right?
Sort of, yes.
Sorta. Can the same be said about the infrared, ultraviolet, X-rays, and all that? Could you heat something up with it, like microwaves?
So
Even
it's
though less.
what each of those wavelengths are doing. Okay, so when we're looking at microwaves, what that's causing things to do is cause water molecules to vibrate. Okay, well, if water molecules vibrate, if anything vibrates enough, what happens? It heats up. Okay? When you move into the different energy forms, when you look at visible light, what's actually happening is we're taking electrons, and we haven't talked about where they exist yet, but we're taking electrons in their nice, happy little ground state home, and we scare the crap out of them up to a higher energy state. Okay? The absorption of energy to get that electron to jump to a higher energy, that's our visible light. When we move to ultraviolet light, we're now giving them even more energy to jump even further. Okay? When we move into X-rays, we're now looking at a different type of nuclear excitation. When you move into gamma rays typically involve the energy released or absorbed by nuclei. Okay? So that's looking at nuclear radiation is typically happening in gamma rays. Okay? Cosmic rays, you're looking even further, larger sources of energy, usually in the interstellar regions. Okay? So each of those energies will do something slightly different, depending on what it's exposed to. There was one and then two.
So basically, certain colors affect the atom differently.
Yes, exactly right.
And in the middle, with the greenish blue, they do everything to the atom at the same time.
So not quite. Each of those does something different. Okay? So if we treat, and we'll see this in just, I might have to come back to this thought, but if we look at stairs, okay, and we say stairs are different places where electrons can exist. If you throw a ball down at the bottom and we give it some energy, let's say we give it red energy, relatively low energy. It's enough energy to kick it up 2 steps. When it falls back down, it bounces a little bit, not a big deal. If we kick it with violet energy, what happens? It goes up a lot further. Okay? So it's not that in the middle we're doing everything. It's in the middle we're not doing as much as the highest. We're not doing, or we're doing more than the lowest. Okay? So it's a different excitation level. Is that? Okay.
I was just curious, like, what would be something that gives off cosmic radiation?
I don't know that one off the top of my head. In all honesty, you're probably looking at suns exploding, galaxies colliding, kind of fun stuff. Okay. Which theoretically we would never want to observe. Okay. At least firsthand. So, the next part of this, which we started to allude to, okay, is that we've run into this concept known as emission line spectrum. So we had electricity, okay, and we had those evacuated tubes. Remember the cathode ray tube? We pumped on them, removed all the gas out of them. Well, somebody then, for some creative reason, decided to put a little bit of gas into it, but put in a very pure, small amount of some gas. Okay, say something like neon. Then they fired up the electric current through it. And now instead of it just kind of doing a random glow, it gives off this brilliant color. It gets an orange color, okay, or a purple color. And what we're looking at there is the excitation pattern for that type of element. Okay? You've seen this before. Neon lights, that's what this is. You're looking at an overall color. What you've done is you've pumped a bunch of electric current into an atom, and that scares the crap out of the atom. It responds to that, and its counter response is this light output that we then envision, or that we see. Okay? And just like with white light, when you look at white light, what light makes, or what colors make up white light? All of them. How do we see that? The Pink Floyd symbol, fair enough. We can look at the prism. The prism will diffract actually all those individual wavelengths out so that we can see them independently. And so if we have different colors coming out of these individual tubes of elemental gas, we can also use a prism to diffract that light out. And if we see a different color, that means we're going to see different combinations or different sections of our visible light. So what we're seeing on here is we're looking at the violet all the way up to the red end of the spectrum. Okay? And one of the interesting observations that came out of this is that when we look at these individual elements, we don't see a continuous spectrum. Say one side being, one section being darker than another. But what we see is lights, individual lights, and everywhere else there's blackness. Okay, so what's happening in the blackness? There's nothing happening in the blackness. So when we look at an individual element and we hit it with these electrons, and we then look at the light that's output, we are only seeing these very particular patterns come out of this. Okay, well, those patterns have to be due to our electrons doing something. Okay? And ultimately what the conclusion that comes out of this is that our electrons are located in individual energetic homes. And they have to be different energy levels, because otherwise we would just see one light, not multiple different colors. So they're in different energies. And when our electrons jump around between those different energy levels, if the energy levels match perfectly, we see the light. Sounded kind of weird. Okay. If the energy levels don't match, the electron does not move, in which case we see nothing, because the electron cannot move between homes unless it has a distinct home to move to. It's kind of an odd observation to make. Okay? Niels Bohr was the one that hypothesized what came out of this. And what he ended up saying, the left shows up a little bit nicer, I'll try and draw it more carefully on here, is that our electrons exist in homes around the nucleus. Okay? And these homes have differing energy levels. And so what ends up happening, particularly when it comes to the atomic line spectrum, is that if we have an electron, which I'll just use an arrow here, in that first energy home, and I give it tons of energy by pumping electric current into it, well, that electron says, oh, I got enough energy, what am I going to do? I'm going to move to a new home. So it now exists up here, leaving a hole behind. Okay, remember when we talked about things, we always strive, I think we talked about this, we strive for neutrality, okay? And neutral things are lower in energy. So what happens when I stop giving that electron energy to move up? It can't stay stationary because it's at a higher energy level. It wants to move to a lower energy level. So what does it do? It releases that energy and drops back down. What does it release that energy as? Light. And that's the color we end up seeing. Okay? What makes this interesting is that we don't see a broad spectrum of lights. We only see individual atomic lines, okay, or line wavelengths out of this. And what that means is that these orbitals, or sorry, these homes, electron homes, have very distinct energy levels. Okay, so let's say the gap between those first two let's say to do that, jump that gap, I need exactly 3 joules of energy. Remember, we talked about joules being a form of energy, or a unit for energy. What happens if I give the electron only 1 joule? Can't make the jump. So where does it sit? Exactly where it is. It does not move. Let's give it 2 joules. Same thing. Doesn't move. We give it 3 joules. Now it can jump. So it'll make that leap up to that next highest energy level.
You make 4, would you go past it, or would you stay there?
We'll address that in a second. Now that it's at this next highest energy level, now we pull the energy away. The energy is no longer provided. The electron says, hey, I'm in a higher energy state. I need to get back to neutrality, back to my lowest energy state. So what does it need to do? Decay back down into that ground state, into that lower energy. But we cannot create or destroy energy. So what happens to that excess energy? It has to get released in some form. And in the case for our neon lights, that form is light energy. So our electric current is just to get things up into the excited state. Once the energy stops hitting that particle, it can move back down to its ground state, and what we see come out of this is light. Okay? That light, okay, or the wavelength of that light, or sorry, the energy of that light will be equal to whatever color we might detect. Okay? So that difference in those levels is what gives us that light pattern. Okay? Questions before we go to Pierre's question? Yeah. Do you have any idea?
Well, since you just gave me 3, I'm saying 3.
Oh, okay. I was just going to make up a number, actually. That's why I was asking if you knew. I have no idea. That, in a 151 class, you would actually calculate the different energy levels. Excuse me. It's tedious, but it isn't that bad. Thankfully, we don't have to deal with it because I don't like the tediousness of the calculation. But it's going to be equivalent to the energy associated with, let's see, did we quantify it back here? It's not quantified here. If you look for an individual light, so let's say that gap corresponded to red energy or red light, what you could now do is say, what is the energy for that wavelength of light? Okay, so this was a formula that you could go through and solve, and its energy equals Planck's constant times frequency, so it's Planck's constant over hc over wavelength. So speed of light times a constant divided by the wavelength. So if we had red light, the wavelength is roughly 650, 700 nanometers. You can add that in and do a calculation to determine the exact energy to make that leap. Okay. You don't need to do that. If you want to do it, talk to me after class. I'll get you some problems.
So this is just used to determine the amount of energy?
Yep. All we're really looking at is, and at this point we aren't even using it to determine the amount of energy. We're trying to use it to see that there is a distinct energy between these. Okay. Which is why when we, oh man, and I deleted all my circles. They were such lovely circles. Give me some credit. This is the second time. I got lazy. Okay. So when we talked about it at first, we said 1 joule, 2 joules, and nothing happened. 3 joules, it jumped, and our electron could make it up to the next energy level. What happens if we hit it with 4 joules? Well, that depends on what the energy level is between these two. Let's say the energy level between those two is 2 joules. If I give my electron 4 joules of energy from the ground state, where is it going to go?
Jumps and stops.
All it can do is jump up to the 3 joule energy. It can move up to the next orbital. It can't go any higher because it doesn't have enough energy. Okay, so what happens to that other joule of energy? Floats on through the rest of space and potentially hits our other electrode. Okay. What happens if we now jump to 5 joules of energy? Now it can jump all the way up to that higher energy level. Okay. And it's those individual steps in between and the line spectrum that come out of this comes to this big conclusion that the electron energy levels are quantized, okay, which is a fancy way of saying that we have distinct, discrete energy levels. Okay, I have energy level 1, 2, 3, 4. I don't have energy level 1.1. We don't have fractional energy levels. We have these very distinct steps within this, which comes back to, I believe, Don, you were asked a question about what happens if we had green light, and I was saying staircases. So what our electron is effectively at is at the lowest level on our staircase, the very bottom. If we give it a little bit of energy, it can jump up one stair. But if we don't give it enough energy to clear that first step, what happens? It just stays there. If I give it enough energy to clear that one step, what does the ball do? It goes up one step. If I give it enough energy to jump up 20 steps, what can it do? Jump up 20 steps. Okay? And that's what's happening within our staircases, and this is our quantum concept-ish for electrons. Our electrons are in orbitals, like a step. Staircase, not steps. Okay, like a staircase, not like a ramp. Okay, so this is continuous versus discrete. Our electrons exist at discrete energy levels, not continuous. Okay, so a ramp is continuous, close enough to spelled right, and our steps are discrete. If we look at the energy spectrum itself, the entire electromagnetic radiation spectrum, is that continuous or discrete? The entire energy spectrum, from cosmic radiation all the way down to radio waves. It's continuous. There's no individual lines. Okay, it's a blurred lines. Man, I didn't think it was that bad. Okay, if we look at the visible spectrum, red, orange, yellow, green, blue, indigo, violet, continuous or discrete? Continuous. Remember, there's no individual line where we say to the left of this line it's red, to the right it's orange. Okay, what we're doing is putting our perception on it and saying mostly red, mostly orange. Okay, so we're looking at a continuous spectrum. This seems kind of odd to us. Okay, as humans, if we look around at all of our things, at light, it's continuous. And yet what happens with our electrons? They're at discrete energy levels. This is kind of an odd phenomenon. It seems a bit weird. Okay? But it's due to this discrete energy levels that we can see these atomic line spectrum. Okay, so that first one I gave you, I think, was hydrogen. Okay, what happens if we change the element? Is that going to change where our electrons exist in different energies? Okay, if we move up to helium, I now have 2 electrons. Do those electrons see each other? Potentially. Okay. Minimally, you could say they see each other and that's why helium gets bigger. Okay. Or you could say that they see a larger nucleus. If they see that larger nucleus, is that going to change the energy of those electrons? It should. Since it changes it, what happens to the line spectrum? It also changes. So what we could do is potentially look at, let's see, hopefully I got this slide right. Oh, son of a... We could look at atomic fingerprints. And within these atomic fingerprints, what's happening is that as we change the element, we've changed the numbers of electrons around our nucleus, we've changed the nucleus, which means the electrons within an individual atom or an element have all changed from another element. Well, if those electron energies have all changed, what happens to the atomic line spectrum? They're now jumping at different energy levels. Okay? And they're discrete energy levels for that individual atom, but they are different from a different atom. What does that mean? That means if I take any element, I can look at its atomic line spectrum and it will be different from any other element. This becomes fascinating when you look at, not space exploration, but space studying.
Atmospheres and exoplanets.
There you go, atmospheres and exoplanets, that works. Or studying other suns. We can look to see what elements are on those planets. How? We look at the light coming from it. And what we can do is separate it out into the line spectrum. And that individual line spectrum can tell us that on that planet, or on that sun, there's a really high concentration of helium. Because the helium atomic line patterns are really, really intense. Okay? Or there's a lot of lithium there because the lithium spectrum is different from the helium. So we can do a lot of these kind of long distance studies and look for those key elemental fingerprints. It's kind of neat. 1, 2.
So is that how astronomers kind of say, oh, we found this planet that's possible, similar to Earth, and yada yada,
Part of it, yes.
you know?
They're looking for other things, but yes, that is part of it. One of our astronomers, I believe, is doing research on trying to find hydrogen. And hydrogen spectrum is not easy to see, apparently. I didn't know, but apparently it's not easy to see.
I was just gonna go along the lines of saying, is that how they like know certain atmospheres and certain planets are poisonous and?
They can do some detection that way, but you have to look for actual high excitation levels, and within the atmosphere you're not getting a lot of high excitations like this. You'd be looking more at suns.
And also, as far as like colorblind goes, is that like the person's interpretation of the light itself, or?
So it's a different system, but it's the same idea. What's happening within your eye is that there are individual molecules that absorb different wavelengths of light. When it absorbs that wavelength of light, it goes, hey, I see this light. Okay, and your brain goes, oh, okay, that's that color light, that's where it's coming from, that's what it looks like. For someone that's colorblind, the molecule that's supposed to absorb that light does not absorb it. So it's sitting there waiting and says, no, I don't see any white. There's no white, or no red. I don't see any red. So it never raises the flag, so your brain never acknowledges the red light.
So would it be like, if someone was colorblind, couldn't see red, but they could see green?
They could see other wavelengths because it's a different molecule absorbing the light.
Red as green? Or they just couldn't see?
Yeah, that's the same idea, that they are picking up some characteristics of the light, but not the stronger ones that give you the different colors. And it's also a slightly different process. What we're looking at here is atomic. For vision, it's actually small molecules. Don, and then...
So if we were to get to the chemistry aspect of astronomy, and we want to see something like outer space, like really far, that's like different wavelengths that we can't really see with naked eye. What would like put a contact lens of an element on the telescope?
So we could go through and put different filters on the telescope to actually filter out and make certain responses. We would then interpret that data as a color. So if you see some fancy outer space photos, sometimes what they'll do is interpret an individual signal as a color. Okay, like infrared goggles. Okay, you can't see infrared, but what the goggles do is detect that infrared energy and turn it into an output that you can recognize and see. Okay? So with those cooler photos that get all those bright, brilliant colors, a lot of that is secondary interpretation. Still cool, but we can't see it.
So I'm just confused, like how you would read it, because I mean there's different numbers of lines on each, but are you focusing
Yes.
on the number of lines and the color, or?
Yes and no. So what we're looking at is that each of those lines represents a jump for an electron from one home to another home. So in helium, there happens to be there's 2 lines there, 3, 4, 5, 6, 7, 8 distinct jumps that happen in the visible spectrum, which is an important distinction. Do all of the jumps have to happen in the visible spectrum? No, they can happen in the infrared and they can also happen in the UV. They typically tend to transition more towards the UV. What we're seeing here just happens to be the jumps where the difference in energy corresponds to a visible light spectrum. All right? And when we move to different atoms, you'll notice that we'll see differing amounts because the orbital energies have now all changed slightly, which now puts them off skew to either give us light, okay, similar light, or not give us any light. Okay, so we don't see that purple transition in lithium. And that's because the electron energy levels in lithium are different than they are for helium. Okay. 1, 2.
I also noticed that the lines are separated differently. Like the reds, they're kind of like for helium, it's spaced out. Is there like a significance for that?
What's the difference between purple and red? What's the difference between purple and red? Has to do with energies. Could also do with wavelengths. Purple is at 400 nanometers. Red is at 700 nanometers. Why do we see a larger gap here?
The energy. Okay.
the energy between those orbitals happens to be different for each of those transitions. So it just so happens that in our purple transition, we have orbitals that are closer energy gaps than they do for the red.
So like when a chameleon changes color, does it absorb energy?
We're definitely opening up a can of worms here, but when we visualize energy, or when we see a chameleon change its color, what's happening is the color that we see is the light that was not absorbed by the chameleon.
So it does, like the chameleon does like absorb light.
It's changing the molecules on its surface to absorb different wavelengths of light in such a way that it can match whatever surface it's on. Yeah, that's pretty crazy. Okay, so this is our evidence for our energy levels. Again, with these stupid circles. I need to change this figure so we get better circles. So when we're looking at, I'm pretty sure this is our hydrogen spectrum. We've got our circles. Okay, these are our different energy levels for our hydrogen atom. Okay, and what they're trying to show within this figure is to see that purple light. That corresponds to a jump from the 5th energy level to the 2nd energy level. So when we put electric energy in, we're taking our electrons from our 1st energy level and we throw them up to the 5th energy level. There is nothing to prevent that electron from coming from the 5th down to the 2nd, or the 5th to the 1st, or the 5th to the 3rd, or the 5th to the 4th. It just so happens that the only one of those transitions that generates visible light is the 5th to the 2nd. And the difference in energy between the 5th and the 2nd orbital in hydrogen happens to be purple light. Yes?
Is there an infinite number of energy rings that the electrons can jump to?
Theoretically, yes, but we definitely run into some maximums. And we can kind of, I think we got a better figure that'll address that in a little bit. So if you blast, well, so that's your limit. Because if you blast the electron clear out of the atom, can it ever relax back down? It's not in the atom anymore. So the different orbital energies are when they're associated with the atom. So theoretically, we can continue to go more higher and higher in energy up to the point where it's no longer added. Okay, so if we looked at a stack of a gap, okay, where this is the highest and this is the lowest, okay, your orbital energies usually jump pretty high at first, and they get progressively smaller and smaller and smaller and smaller until you're splitting hairs as far as differences in energies. Those energies are now so close to being referred to in the vacuum or not attached to the atom that while theoretically we have those orbitals, the electron would probably just fall out of it.
Is there less energy by the nucleus?
Less energy closer to the nucleus. Good question.
As you go out, you get more energy?
Why would the energy why would it be less energetic to be closer to the nucleus than to be further from the nucleus? Why is it lower in energy to be closer to the nucleus than further from the nucleus? No.
Because of the charge difference, like potential energy go
Charge.
the farther you go from it.
That's all it is charge. If we take that negative charge and we bring it closer to the positive charge, they're starting to neutralize each other. What happens is I take that negative charge and I move it further away from the positive charge. It can't neutralize anymore. And I'm now looking at a larger negative charge, or less neutral. Less neutral, higher in energy. Okay? I'm not sure if I should continue back with this topic, but we'll go through and do it anyway. For our hydrogen, our blue-green wavelength is now a jump from our energy level 4 to energy level 2. Okay. For our red wavelength, it happens to be energy level 3 to energy level 2. Why is energy level 3 to energy level 2 as opposed to 5 to 2? Why is the jump between, for violet, a larger jump? 5 to 2 versus 3 to 2. It's more energy. That's a bigger distance. You have to drop a lot further in energy. To go from 5 to 2, we're going from a very high energy state to a relatively low energy state. Well, that difference in energy has to be emitted somehow. What's that emission? The highest energy electromagnetic we can, which would be, in this case, violet. That's why our purple's a larger jump, because it's a higher energy light. Are you guys getting this? Because I don't know, you're getting some kind of crazy questions that make me going like, wow, you're thinking about this kind of way out there. It's kind of surprising me.
Can there be multiple jumps at the same time?
Not within reason.
Oh, okay.
Yeah.
So it's all like in sequence or randomly? Okay.
Yeah, so when we're looking at, I see your hand, give me a sec. When we're looking at an individual spectrum, that's not saying a single atom is absorbing that, because a single atom will only absorb one energy, and it will emit that one energy. So when we look at the spectrum and see all of that, we're exciting a massive amount of those individual atoms. Okay, we're looking on the orders of billions or septillions of atoms. Okay? And it's that massive excitation that's generating each of those individual colors. And since we're constantly putting electrons in it, once the electron jumps up and comes back down, another energy source can come in and cause the electron to jump again. Okay? And it's each of those drops across the thousands of possible iterations that generates the spectrum.
Does it have anything to do with speed?
No, don't worry about speed.
Okay, so when they're trying to find out the atomic fingerprint type of things, do they just give it a really big charge and then see where it falls?
So to get those individual atomic fingerprints, what we're looking at here, is what you have to do is get that element into a gas phase. Once it's in a gas phase, you can then pump electric current through it. That electric current is your energy source that can then absorb and actually either do the emission or not.
So for each element, there's certain sections that picks up the wave. That's where those different colors come in at certain
There are electrons within each element that can absorb that energy and jump to different energy levels.
and that's where that fingerprint comes from.
And that's where the fingerprint comes from, it returning to its ground state. Yeah. So the excitation gets it separated up. It's the returning down that gives you the light. Yes, then yes.
How do you get a metal to like a gas phase?
Carefully. High or lots of heat or extremely reduced pressure.
Does that mean that these measurements would be just approximate, because we're measuring how?
These are actual spectra. So,
2 feet?
yep.
Does that mean people were just blasting different energy levels and they found reactions?
So what's happening with electric current is that electric current supplies a ton of energy, enough energy to completely overwhelm all of this. So your electrons are now jumping all over the place within an individual atom. Okay? Whenever they relax back down, right, is your emission of energy or your emission of light. So if you take 1,000 different people and you punch each of them, okay, they're all going to move different distances. Okay? The average distance that you pick up out of that would be kind of what you're seeing with your atomic line spectrum. That was kind of violent. I apologize for that. So, this is what's happening within Bohr's model. So now it's when we're going to kind of step this up and get a little freaky with it. So we've got these different energy levels. Okay, so that's what we're showing on the left here. So as we go up, let me add one more here. Yeah, okay. As we go up, we increase in energy. Eventually what happens, we reach the vacuum. Okay, and in the vacuum, our electron is no longer associated with the atom. Okay, so we can't have an electron existing in a home with the atom if it's in the vacuum, because the vacuum means it's not with the atom anymore. Okay, so what Bohr then theorized was that we had different energy levels for our electrons. So we start at a very low energy, and we slowly move our way up. Okay, and you'll notice that the gaps between those are different. Why might the gaps between those be different? What's that? actually related to space. If you get very close to the atom, what's the surface area? Very close to a marble. What's the surface area on the marble? Pick some number. I don't care. Any number. 20. What happens if we now move to a basketball? What happened to the surface area? Okay, it went up significantly. And if we went up to the planet, okay, even more surface area. So what's happening as we move up in energy levels is our electrons are getting further from the nucleus. Well, as they get further from the nucleus, they have more surface area in which to exist. Which means if I'm going to look at the distance between those first two energy levels, those are really close to each other. So I need to push that second energy level a little bit further out so that we have a proper space distance between them. As we get further and further up, we don't need to push quite as far out because there's now more surface area for where the electrons could exist on the outside of that. That is a rough approximation. Okay? How many lines do I got? 1, 2. I got 8. Let's make one quick adjustment here. This energy level right here is the vacuum. So how many different energy levels have I got shown here then, if we ignore the vacuum? Because we can't exist there. 7. Any ideas why I might have picked 7? What am I pointing at? Periodic table. Where do we get 7 in our periodic table? It's the number of rows in our periodic table. In our lowest energy level, we can refer to it, it almost always gets referred to as N. But our lowest energy level is the first row at the top of our periodic table. That is the absolute lowest in energy. In our second energy level, what have we done? We move to the second row. Third energy level, third row. Fourth energy level, sort of fourth row. Right? Fifth energy level, sort of fifth row. We'll talk about the sort in a little bit too. Right? So what's happening is we've now established different energy levels for where our electrons can exist. Right, so now let's bring in the thought of, well, how many electrons can I fit into an energy level? Right, so let's look at that lowest energy state. How many electrons should I theoretically be able to put in that energy level? Okay, 1 or 2. I want an explanation for either answer, because both of those I can accept. No ideas? What charge is an electron? Negative. What happens when you get an electron near an electron? They repel. So how many electrons could I theoretically put in one orbital then? 1, because if I put in a second, what happens? It repels away. So 1's a possible answer. What's the other answer? Look at that first energy level on our periodic table. How many electrons can fit in that? First energy level, at the very top. 1 and 2, because helium is in that second row. Okay? So that brings up an interesting dilemma then. How can I fit a second electron in if all it does is repel? Okay? It's not that it's stationary. It turns out that our electrons have a spin associated with them. And I don't expect you to understand that, but there's a particular spin, clockwise or counterclockwise. So our electrons can kind of counteract that repulsion by spinning opposite directions. Very, very weird. Okay? But what ends up happening is an individual orbital can fit 2 electrons. Okay? And we usually represent that spin with an arrow, okay? Either up or down. Yes?
So these different levels, are they on different pivoting points, like a gyroscope?
Not like a gyroscope.
So like they're just in one.
I really wish I could give you a physical explanation that you could somehow wrap your brain around. There is no physical explanation that you can wrap your brain around. Unfortunately, you can't do a direct comparison to something else. Yeah, I sorry I can't give you a better answer, but that's all you got.
Well, wouldn't it be like floating magnets? Like you had 2 magnets that were balls and you spin them, they actually start spinning
Spin is just a word that they chose.
Okay.
Talk to me after class about the spinning magnets. I've never heard of that before. That could be something interesting. The spin state is not necessarily just a word. It's sort of a word that we chose. It's a little bit more complex than that. Okay. So if we run under this assumption, so we get back to our orbitals, we said each of these energy levels can hold 2 electrons. So we move up to this energy level. How many electrons? 2. How about that one? 2. How many energy levels did we say we had? 7. So how many total electrons? 14. Huh. How many electrons does silver have? What's the symbol for silver? Ag. How many electrons does neutral silver have? 47. But I only came up with 14 electrons in my orbital diagram. What the heck is going on here? This is a bit weird. Right? As we move up in energy, what we found is that the electron starts to change its ability to exist, or where it can exist. Okay? Mind-boggling. When we move up to the second energy level, how many electrons can fit in that second energy level? And notice I'm not saying orbitals are homes, just in the second energy level. How many electrons can exist? Okay. So to count this, what we need to do is look across row 2. How many columns do we have? How many electrons can fit? 8 electrons. Okay. As we move up in energy levels, we start to increase the capacity for the electrons. But this seems odd. This is counter to what we would understand. Within an individual orbital or an individual location, I would assume I can only put 2 electrons. And what ends up happening is that each of those energy levels subdivides into new locations to put electrons. Okay. At energy level 1, there is only one place to put electrons, which is why at that n equals 1, our first row, we can only fit 2 electrons. But when we jump up to the second energy level, it splits now. And now there's not just one location to put electrons. How many locations are there? Remember, each energy or each orbital or each home can only hold 2 electrons. So if we got 8 electrons, that splits out into 4 homes so that we can fit all 8 electrons. Okay, well, those homes we need to come up with a name for. Okay? And that's where this starts to get a bit dodgy. Okay? So I'm trying to color code this as best we can. So our lowest energy level, n equals 1 with our black. Okay? We only have one possible system. When we jump up in energy level, we now increase our possible locations. There end up now being 2 possible locations that I can put the electron. This still doesn't quite add up right, but we'll get into that. Okay? What we're saying is we now have a type of orbital. The energy level of our orbital, and now the type. Okay? When we move up to n equals 3, what happens? You get 3 types. And if we look at the diagram that I've got shown here, I'm trying to show those 3 types. Okay? So those types give us more places to put electrons. That's still not going to account for the complexity and the amount of electrons in our periodic table. Okay? So there's yet another tier to this. See, did I actually do it nicely on this? Oh, and my computer's dying, so I can't see that. We get an orbital orientation, so I didn't do it nicely. Okay? In the orbital orientation, we can now take each one of those orbitals and see if there's a different axis I can move it to. If it looks different, I have a new orientation. Okay, so let's bring in something about what these orbitals look like. Okay, for n equals 1, our orbital looks like this. Okay, and if you want to make me get real fancy on it. It's not a smiley face. Really? Is it that bad? Okay, fine. I'll just go back to the normal shape. Remember, these are three-dimensional. What do we have? A sphere. You take that sphere and you turn it. Can you tell that you turned it? No. How many orientations are there for a sphere? 1. For n equals 1, our first energy level, how many electrons can we possibly fit? Only 2, because there's only one type of orbital, and there's only one orientation for that orbital, because all the orientations look exactly the same. Okay? When we move up to the second energy level, we're going to now repeat what we had on the first. So I'm going to have another sphere. Well, how many possible ways can I orient that sphere and have it look different? None. We move up to the next energy level. I'm going to have to give myself some space here. We have this dumbbell shape. Or sorry, the next orbital type. Okay, well, if I take that orbital and I rotate it 90 degrees, can you tell that it was rotated? Yeah, there's a second orientation. Rotate another 90. Can you tell it was rotated? There's another orientation. There are 3, and don't get all fancy with me saying there's more orientations. There are. Keep it simple. We get 3 main axes on which we can orient that orbital. So there are now 3 possible categories. Okay? So when we move to the second energy level, I have a total of 4 orbitals. 1, 2, 3, 4. How many electrons can I fit in total 4 orbitals? 8. How many columns in the periodic table for that second energy level? 8. Holy crap. The periodic table has information about electron holes? Yes, it absolutely does. What happens if we move up to n equals 3? Okay. We're going to repeat what we had before. We had the sphere. We've got our dumbbell and our new shape. Oof, close enough. Okay. I actually need more space. Is this goofy looking clover leaf? Oh, yeah. And it turns out that we get 1, 2, 3, 4, 5 possible orientations when we move to that energy level. Which means how many electrons can we possibly fit into the third energy level? 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons into that third energy level. Move to the third row. How many columns do you see? Yeah, this is where we went into that sort of. Okay. The transition elements, this row, the first row of our transition elements, is actually at the third energy level. Not a whole lot else I can tell you about that. It is actually at the third energy level. Okay. It is offset because of how electrons get put into an atom, and we will talk about that probably on Thursday, but we'll see how far we get. Okay? So include that row in your count for the third energy level. How many columns are there? 18. How many electrons did we say we could fit in that third energy level? 18. Thank goodness I could do math. There it is. Our periodic table is accounting for where electrons can exist within an atom. All of these references that we're making are ultimately just saying something about the home. Where can an electron be happy? Okay? And we talked about the last part of this, the electron spin. That's why we could get 2 electrons into each orbital. Okay? And we talked about that way up at the beginning, but ultimately it comes in at the end. For those of you moving into 151, if it wasn't confusing enough, the energy level gets referred to as N. The orbital type gets referred to as L. The orbital orientation gets referred to as M sub L. The electron spin gets referred to as M sub S. Lucky for you. Okay? And then you have to know all those correlations. As far as what I expect you to get out of this, you need to know for an individual type of orbital what orientations are possible. Why? Because that tells you how many electrons you can fit in that type of orbital. Okay? So it gives you information about where your electrons can exist. And in all of this, all we're really trying to do is come up with an address. Right? If you think about your address, you write out an address or to a friend, snail mail, all that fun stuff. Okay? You write your name on it. Right? That's like the spin state, getting super specific on who exactly in that house the letter is designed for. Okay? Then you've got the number and the address, okay? Or the street name. Okay? You're getting a little bit less specific now about exactly where that needs to go. Then you can move to the city. Then you can move to the state. You can move to the country. Each of these subsections is effectively a division of that. Our energy level is what country does that letter need to go? The orbital type is what state? The orbital orientation, we're running out of options really fast. What county, which isn't getting very specific enough. Okay, we might have to county, city, street, thank you, person. Okay, so it's an address. Okay. Try to avoid getting too bogged down in the details of it. It's just an address. That's what we're trying to say, is where can that electron exist? And we need to be as referencing as cleanly as possible when we go through and do this. So if I want to reference this guy right here, or let me point to a different spot, this home, how can I reference that home? What can you tell me about that home? It's an energy level 2. That's what I'm waiting for. Orbital type. Oh, we're coming up with some number systems here. Okay. Why don't you just tell me it's orbital type dumbbell? Okay. That's kind of a tedious system to use. So what do we use instead? Energy level 2, we quantified those. We dropped in numbers. We said 1, 2, okay, 3. If we bring in numbers to reference our orbital types, that's going to get a bit weird, because then we'll say it's 2, 1. Is that 2, 1, or is that 21? All right, so instead of using another number, let's use a letter system. What would be a reasonable letter system? Maybe A, B, C, D, like, alphabetical, makes sense. Sorry. That sphere one is referred to as S. This one actually kind of makes sense. Why is it referred to as S? Because it's made out of a sphere. Hey. So if we moved up to the second energy level, that first circular one is an S. We moved up to that next shape. What's that next shape referred to as? Figure 8, but we want a letter. Did you really just say the answer? Good job. P. Move up to the next one. D. So if I want to reference that orbital that we've got the arrow to, that is a 2p orbital. 2 referencing the energy level that we're at, and p referencing the orbital type. What happens if I want to reference this one? Green was probably a bad choice. Let's try that arrow again. What is that one now? What energy level is it at? 3. What orbital type is it? P. I now have a way to reference each of those locations, and now I can say where my electrons exist. Okay? So it's just to our electron homes. There's all that city straight. So let's go back to these orbital types. We just kind of walked through these. Okay? These are the individual shapes that you may end up seeing. What these shapes represent is a 95% probability of finding the electron. Okay? This does not mean the electron zips around that sphere like a sphere. No, it jumps all over the place. But 95% of the time it's found within that sphere. So sometimes you may see this drawn out where there's a bunch of a dot pattern. Okay, so if we dot pattern that all the way across, you'll notice that most of those are supposed to be dots. Dots are happening within that sphere. That does not mean a dot can't happen out here. It just means 95% of the time it's in that sphere. Okay? So that's where we came up with these shapes. They are mathematical solves of the quantum physics behind where this came from. Okay? So what we just want to do is recognize these as shapes. And we want to come up with common or consistent terminologies so that we always know what we're referencing. So a question could be, what is the S shape? Well, number one, you need to know what the S shape was. What did we say the S shape was? Which one of these? First, second, or third? First. So that's our S shape. What shape do we refer to that as? Sphere. The P shape was? Or a dumbbell. Let's try that again. Dumbbell. Uh-oh. Just call it dumb. Last shape is our d orbital. And our d orbital is typically referred to as the, pretty close, cloverleaf. Okay. Okay, as the note kind of alludes to, it is amazing to watch someone actually derive this from the quantum physics and the mathematics. It's absolutely fascinating. They can punch it all through and they solve it. And, oh, this is this number, this is this number. It's nuts. Okay? I can't do it. Don't ask me to do it. I'm not even going to pretend I can do it. Okay? But these are kind of the shapes that you need to come up out of this. Okay? So our orientation, as we already talked about, with that s orbital, there's only one possible orientation. So there isn't a new viewpoint. It's just the s. It's just the sphere. That's it. But what happens when we move up to the p orbital? Well, the p orbital right now is oriented along what axis are they saying that is? I think it's the x. Okay. Could we orient it on a different axis? Yeah, we've got the y, and we have the z. So that gives us three possible orientations. Okay. Each of those orientations is an orbital, which means I can fit 2 electrons into each of those. Okay. When we move up to the d orbital, this is where we get the cloverleaf. Okay. This one's even more bizarre. Okay. There's different axes under which you can put this one around. There are all your possible axes. Except you'll notice that last one really doesn't look like much of a cloverleaf. Okay, it's not supposed to. What does that shape come from? It comes again from the quantum physics of having to solve these things. So what you're responsible for doing is acknowledging what the shapes look like and what do we call them. So if you see the sphere, you know to call that a S. If you see this weird dumbbell donut, it's the d orbital. I think it is called a dumbbell donut, but not sure on that. Donut. Because it's got a donut around the dumbbell. Okay? So you're responsible for acknowledging those things and just seeing them. Okay? And recognizing those patterns. Yes?
How was the last one, the dumbbell donut when that was in cloverleaf? Can you describe it?
So it comes out of the physics on where the electrons can exist probability-wise. One of the equivalent shapes that comes out of it is that last one in the lane, which is a little bit weird. It's kind of your odd one out. Okay, so what you'll be expected to answer is cloverleaf. The dumbbell donut is more 151 material. Okay. We'll kind of whip through this fast, and then we'll start with it again on Thursday. So with the first energy level, we have just the s orbital, which means how many electrons can we put? 2. So we can only put 2 electrons all the way across. So within our sublevel, we can only put in 2 because it's the s orbital. The s orbital can only hold 2 electrons. So the total electrons for that energy level is just 2. What happens when we jump to the second energy level? What are our sublevels? We have the 2s and the 2p. We're in the second energy level. How many electrons can fit into an s-type orbital? 2. How many electrons can fit into the p sublevel? Careful, this is 6. We're going into the sublevel. There were 3 orientations. Each of those orientations fits 2 electrons. So as our total electron count in the energy level is 8. Okay? So we could break that all down. Whoa, come back here. And that's what we end up seeing out of your textbook.
What's F? What's your?
I'm out of time, oh well.